All right, a super simple test for convergence involves what's called a P series. It will be even easier to apply than the geometric test, as you'll see. So our series has to look like this. We got the sum from n equals 1 to infinity of 1 over n raised to some p power, and this p has to be a positive constant. It cannot be 0. If it was 0, then this would be n raised to the 0 power, which is 1, and you would be adding up an infinite number of 1s, which is super big. P can't also be negative, because it was negative. Then this n would actually shoot up to the top, and it would get infinitely big too. As a matter of fact, it would diverge by the nth term test for divergence, okay? So we're talking about any positive constant, whether that be integers or fractions like 1/2 or something like that, right? So an example of a P series is the harmonic series. It happens when P is equal to 1. Reason why it's called a harmonic series, because it's named after the points on vibrating strings that produce multiples of its vibrating or its fundamental frequency. So here we have a given wavelength. If I cut that wavelength in half, I double the fundamental frequency and so on. I'm pretty sure that this was a property of vibrating strings that was discovered by that guy, Pythagoras. Okay, so here again is the harmonic series when our p-value, our power, is equal to 1. So we have 1 plus a half plus a third plus a fourth. And this is what we started the whole entire lesson with. If we take a look at the nth term test for divergence, it told us nothing because, yes, these terms are getting closer and closer to 0. So we're going to perform basically the integral test on the entire P series and see what it takes for that power P for the series to converge or diverge, right? So that's what we're about to do. We're going to apply the integral test. So we have to replace our discrete series with a continuous positive and decreasing function, and then apply the integral test. Remember, that takes 3 conditions. We have to make sure that our function is positive, and that it is decreasing, and that it's continuous. Let's do it. Okay. So, for our P series test, we are replacing our series from n equals 1 to infinity of 1 over n raised to the p power. And now, understand that the p is a constant. So it's a power that's going to stay exactly the same. It's the base there, the n, that's changing, which is different from geometric, which is kind of the reverse. On geometric, it's the base that stays the same. Where's my laser pointer? There it is. It's my base which stays the same, and it's the power which changes, right? Okay. Whoa, what the? Hold laser tail? Let me see what the heck that does. Fascinating. Okay, anyway. All right, so then we're going to replace that with a function, f of x is equal to 1 over x raised to the p power, right? And now we're going to apply each one of the conditions, or check to make sure that each one of the conditions are met. And the first one is positivity. Is it positive? Question mark. All right, so we've got f of x is equal to 1 over x raised to the p. Okay, so p is a positive constant. X is starting at the number 1. X is greater than or equal to 1. So if we take a positive number and we raise it to some positive power, this thing is always going to be positive. So, whoops, here, let me actually move this over and say this is greater than 0. It's positive for x greater than or equal to 1. So our first condition has been met. Let's check to see if this thing is continuous. So f of x is equal to 1 over x to the p. Well, the only place where this thing has an asymptote is where x is equal to 0. Everywhere else, it's perfectly okay. So this thing is continuous for x is greater than or equal to 1, and that's where we needed it to be. All right, and then the last condition, wait a minute, this needs a magenta check mark. And then our last condition, of course, is things got to be decreasing. So we will take its derivative. To take its derivative, I'm going to rewrite the thing first as x to the negative p power, and then apply the power rule to this thing. It'll be a negative p x to the negative p minus 1. All right, so in order to be able to tell if this thing is positive or negative, I'm going to rewrite that exponent a little bit here. Negative p is going to stick around, and I'm going to factor out a negative from this exponent, and it will be p plus 1. All right, so now that the x has a negative exponent, I'm going to put it down in the bottom, x to the p plus 1. All right, and then observe that this term here is always a positive number. Always greater than 0. Our p was a positive constant by the conditions of the actual p series test, and we're just multiplying it all by a negative, which makes this thing less than 0 for x is greater than or equal to 1. Right? I mean, for all values of x, but whatever. Okay, all values of x that we're saying is greater than or equal to 1. Then we have met all of the criteria. I think this is missing something. Oh, wait. I have not stated that it's decreasing. All I said that was its first derivative is negative. So since f prime of x is less than 0, for x is greater than or equal to 0, then f of x is decreasing on that same interval. Okay, there we go. Now we can apply the actual integral test. So to apply the integral test, we're going to take the improper integral from 1 to infinity of 1 over x to the p dx, turn that thing into a limit as b goes to infinity, 1 to b, 1 over x to the p dx. Okay, whenever we go to take the antiderivative of 1 over x to the p, I should be using the power rule unless p is equal to 1. If p is equal to 1, then this thing is just 1 over x, which is natural log. So I actually have to break this up into two cases, when p is equal to 1 and when p is not equal to 1. So let's do p equaling 1 for our first case. So number 1, case 1, p equals 1. If p is equal to 1, then we have the limit as b goes to infinity of definite integral from 1 to b, 1 over x dx. That's the antiderivative of that, of course, is the natural log. Limit b goes to infinity of the natural log of the absolute value of x. I feel like we've done this before. 1 to b, which is equal to the limit b goes to infinity, natural log absolute value of b, minus the natural log of the absolute value of 1, which is 1, 0. And that one, as we've seen before, diverges. Right? I plug in an infinity in our natural log thing. That thing's going to shoot off to infinity. Doesn't matter if we're subtracting 0 from it or not. So, okay. Since, let's see, f of x equals 1 over x is positive, continuous, and decreasing for x is greater than or equal to 1, and definite integral from 1 to infinity of 1 over x dx diverges, then this sum, this is the P series, this is the first case, n equals 1 to infinity of 1 over n also diverges by the integral test. Okay, and this is actually a result that you want to basically memorize. Which case did we just basically prove? It was when p is equal to 1, and when p is equal to 1, remember that this is the harmonic series. And on the AP Calculus exam, it is perfectly acceptable to just point out, oh, you've got the harmonic series which diverges. You don't have to apply any kind of test to it. It's just known. Just known. Oh, wait, let's see. Case 2 is going to be green. Okay, so we've got case number 2. That's when p is not 1. When p is not 1, then we can just apply the power rule for antiderivatives. We've got the limit as b goes to infinity, definite integral from 1 to b, 1 over x to the p dx. Again, we're going to apply the power rule to that for its antiderivative. I would have, let's see, maybe I rewrite that thing to x to the negative p. Right? So I have to add 1 to the exponent and then divide by that new exponent. So it would be x to the negative p plus 1 over negative p plus 1 from 1 to b. Boop, boop, equal sign. All right, and then before I go to plug in my b and my 1, I'm going to rewrite this, clean this thing up algebraically. I'm going to factor out a negative from both the top and the bottom, like on the top from the exponent. So negative parentheses p minus 1. And on the bottom, I'll do the same thing, negative parentheses p minus 1. Evaluated from 1 to b. Okay, keep rewriting. It's essential. So the top part of this, of course, is going to go down to the bottom because it has a negative exponent. So I have a negative 1 over p minus 1. That's me rewriting the negative p minus 1 on the bottom. Times 1 over x to the p minus 1. Evaluated from 1 to b. And I left it like that because the fraction that's right up front here is not affected by the limit at all, because the limit only is going to involve a b, which is going to replace the x that's in there. So I'm going to leave that on the outside whenever I deal with this limit. Okay, so I've got negative 1 over p minus 1 times 1 over b to the p minus 1 minus, when I stick in 1 here, it doesn't matter what your p-value is going to be. Its O is going to be equal to a 1. Okay. And now we're going to go ahead and take the take the limit of this guy. And when I take the limit of this as b goes to infinity, well, it kind of depends on what the value of p is going to be, right? All right, so let's take a look at that term in particular. Oh, what did you just do? Okay, yeah, that's better. All right. The b is what's changing here. It's the base. And now whether or not this thing shoots off to infinity or not depends on the exponent that we have. It's this p minus 1 for this exponent. Because if p minus 1 is greater than 0, if it's greater than 0, then that term is going to stay down at the bottom, and I would have 1 over infinity, which means that term is going to go to 0, right? So if I solve this, that gives me p is greater than 1. When p is greater than 1, this thing is going to converge. When p is greater than 1, then the limit as b goes to infinity, that looks like rubbish, negative 1 over p minus 1 times 1 over b p minus 1 converges. And if it converges, and just like we talked about on the other parts of the integral test, then we would conclude that also the series converges. Maybe highlight this. It converges then. Okay, but what if it was negative, right? It is possible that our power here is negative because we're subtracting 1 from it. And so we've got when I have p minus 1 is less than 0 whenever I add the 1 over. If p is less than 1, then this thing is going to diverge. And the reason why it's going to diverge is because the exponent, again, would be negative. Oh yeah, let me turn off this trace thingy. Yeah, the exponent is going to be negative, which means it's going to shoot up to the top. And when we plug in our infinity for a b, it's going to shoot off to infinity, and it won't matter that we subtract 1 from this thing. All right? Now, remember that we said that we are making the condition that p is all along greater than 0, right? Because if p was originally negative, then that exponent would bring the term in up to the top, and it would automatically diverge. Okay, so let me come back to the slideshow, and let's recap this thing. Okay, so using the integral test, we can show that our function is positive. It is definitely continuous everywhere greater than or equal to 1. It is decreasing. I know it's decreasing because we took the first derivative of that thing. And for x greater than or equal to 1, that thing is less than 0, which means f is decreasing. Check, check, check. And then whenever we do the integral test on this, on the improper integral, we saw a couple of different cases here. We know that the p-series is going to converge as long as your p-value, your power, is greater than 1. But it's going to diverge if your p-value is between 0 and 1, and it includes the number 1. Remember, 1 is the harmonic case. And notice that this is sorta, kinda, the reverse of the test for whether or not a geometric series converges. Because if we were talking about our common ratio being greater than 1, we would know that that thing diverged. But if it was between 0 and 1, it would converge. Of course, a difference between this test and the other test is that if your geometric series was, your common ratio was equal to 1, it actually diverges. And your common ratio can also be negative. Here, your p cannot be negative. All right, so here is the formal statement for the convergence of a p-series. So we have a p-series defined, summation from n equals 1 to infinity. 1 over n raised to the p is equal to 1 over 1 to the p, 2 to the p, 3 to the p, and so on. We know that this thing converges as long as p is greater than 1. And again, just like, because we basically use the integral test in order to show that this is true, just because our p-value is greater than 1 doesn't mean that we know necessarily what it converges to, only that it converges, okay? And then we know that it diverges if our p-value is between 0 and 1, including the number 1. Did you write something down for that? Excellent, fantastic. Okay,